Okay. Hello, everybody. Hi, Steve. Okay. Looks like we got a bunch of participants in here. And Anna's in here too. Anna, let me see if I can promote you. Okay. You can unmute your mic if you like. All right. So let's. Okay, great. I see a bunch of people. Michaela, Comfort, all these new names. Good. Katie Winchester. Um, let's get going. We have a fairly simple presentation to go through today. It's going to be in Keynote, and so let's get to it. What we're going to do is mainly work on a thermal equilibrium calculation. All right, and we'll discuss where you should be today. You should be at the end of the YouTube emergency diversion page, up to the end of up until exam 3, the yellow bar across the top. I want to encourage everybody and admonish everyone to get your homework squared away. And I noticed that not everybody's got homework in, and so you better get on the stick. We have an exam coming up on Tuesday. And so what Tuesday is going to be a little bit different. We won't have a Zoom session in the afternoon. Okay. We will have the exam, and I think I have it set for either 8 or 10 o'clock in the morning. So you'll be able to get an early start on the exam. Now it'll be 70 minutes, just like in lecture, but it'll be here in web courses. And you all are familiar with how homework goes. It's just like a big homework assignment, except that you only get one attempt. Okay. And so you got to make it count. And also, I usually configure it so you only have one question at a time. Now, another thing I want to mention to you is matching questions. If there'll be some matching on there, and matching questions, if there are like 4 matching items for you to choose, that will be 4 points, but it will be counted as one question. So it's like a 4-point question, even though it's just 1 point at a time. The calculations as well at the end of the test, if there are any, will be those will be multiple points, 2 or 3 points maybe, depending on what calculation you have. Right, so be ready for that. So it's going to be 50 points, but it might not be 50 questions because some of them are multiple points. Also, in regard to exam 3, I'm going to put a single bonus question in a separate mini exam. Okay, it's going to be a bonus brain burner, and it's going to be optional, but it will allow you to earn a few bonus points. So it might be like a 3-point calculation. If you get it right, you get 3 points, 3 bonus points. So the 50 regular points will be in the main part of exam 3. And then the bonus nugget will be in a separate one and it will release after you take exam 1 or exam 3. So do your exam 3 first, then you can try the bonus nugget if you like, and maybe earn 3 points or 4, however many points I make it for the bonus problem. Okay. Now let me take a look at chat and go ahead and ask a question about exam 3 if you have any. Can you guys hear that I have a sore throat? I'm really worried. My wife took my temperature this morning, but it's okay. So, hi, Fernando. One new message. Let me look at this. Okay, here we go. How long would we get for the bonus nugget? I haven't decided, maybe 15 or 20 minutes, something like that. The bonus, I'll make the bonus due a little bit later. So the regular part of the exam will be due at 11:59 on a Tuesday night. That's normal. And your homework is due 11:59 on Monday night. So make sure you get all that stuff done. But I'll probably make the bonus nugget um, available until maybe 2 a.m. so that students that take the midterm late will then be able to go and do the bonus nugget. All right, I think that would work out pretty good. Okay, thanks, Sophie. I'm feeling all right now, but I just get nervous about having a sore throat. How our lives have changed. A sore throat normally doesn't bother a person, but anyway. Closing time of the test, 11:59 p.m. as always. My question, Audra Spence. Yes, it's not set to get one shot at each question. It'll be one question at a time, but you will be able to backtrack and re-answer something. So that's good. Okay, Michaela, are there any specific? No, focus on everything, Michaela. I can't really tell you what's going to be on the test, so just focus on everything. All right. Yeah. So, yeah, one question at a time, but you can go back and, you can go back and go over all your questions if you have time. But you'll have to hustle. I mean, it's not like, a nice day in the park. You'll have to really be efficient. Okay. All right. Let's go to. Let's talk about the thermal equilibrium problem. Now we've got a couple thermal equilibrium problems on homework 12 and homework 13. And so this one is a picture from one of the homeworks. Substance H and substance R. Substance R is the hot stuff. Substance H is the cooler stuff. And the question is, where does the thermal equilibrium temperature hold? Okay. So I'm giving you an example parallel to the stuff that you'll be doing with, the homeworks. So for instance, I know a lot of you guys have been working on the tea and honey problem. Okay. So this doesn't look like the tea and the honey problem, but the same decisions you make will help you with the tea and honey problem. So here are the, and I just made up some numbers. So you might not see these when you get to the homeworks and stuff, but you'll see numbers like this and you'll be able to calculate like we're about to calculate. So for the mass of substance H, 30 grams, substance R, a little bit heavier, 41 grams. All right. And the made up specific heats for substance H and substance R are 0.828 calories per gram Kelvin for substance H and 0.336 calories per gram Kelvin for substance R. Now, the substance R is a little bit easier to heat up, but you have a little bit more of it. So it's, you just have to, work it out to which one's going to cool off more and which one's going to heat up more, because you're probably not going to meet in the middle. And here are the two temperatures. Substance H is 805 Kelvin, so it's kind of hot. Substance R is even hotter, 922 Kelvin. And so the initial temperature gap, this is what I want to emphasize today. The gap between those two temperatures is 117 Kelvin. So what that means is that as substance H warms up, it's going to narrow the gap. And as substance H warms up, substance R will cool down. And that will narrow the gap a little bit more. And I'll show you a graphic of that in a second. So basically, what we're going to do here to narrow the gap is we're going to take a few small steps by exchanging a little bit of heat energy, plus or minus delta Q, which is how nature works. You know, nature exchanges very, very tiny amounts of heat energy between the hot substance and the cool substance absorbing and the warm substance losing. And you can make a guess, you know, to get across that gap and find where the two temperatures meet. You can use any delta Q that you want. Okay, and so what we're going to do is let's go and look at here's the temperature gap. We're going to use a horizontal line to represent that. And over here, can you see my cursor going? Yeah. Okay. Good. So you know, substance H starts over here, but it's going to move to the right into a higher temperature. Substance R starts at 922, but it's going to dip to the left a little bit as it cools down. All right, so let's do a bigger version of that. Actually, so what we're trying to figure out is the equilibrium temperature. Is it going to be closer to 805, or is it going to be, you know, somewhere near the middle like that? Or is it going to be closer to 922? That's what we're trying to figure out. And we're going to try to get it to the nearest Kelvin. Okay, you can be more precise if you feel like it, but nearest Kelvin is good enough for our task. Okay, so I just decided let's try 250 calories as a first guess, right? And so we're going to use the heating up equation, Q equals mc delta T, for substance H that gains 250 and for substance R that loses 250. All right, and so let's just start it. Okay, let's start with substance H. Right. So the heat up equation, Q equals mc delta T. Q is 250 calories positive. It's gaining heat. It has 30 grams of mass and a specific heat of 0.828. And we're trying to figure out the change of temperature for substance H, delta T subscript H. All right, now 30 times 0.828 is 24.84, right? And it's calories per gram, calories per Kelvin. The grams cancel out. And so to get delta T subscript H, the change when you exchange 250 calories, the temperature changes. And we want to figure that out, get it by itself. So we divide both sides by 24.84 calories per gram. Now notice that the calories cancel out in that quotient. And the denominator has a denominator, kelvins. And so that flips into the numerator. And then you have 250 divided by 24.84, and that works out to about 10.1 Kelvin, right? So when you exchange 250 calories, H warms up by 10.1 Kelvin, right? So it's going to start at 805, and then it's going to go up, and we'll map that out on the horizontal line in just a minute. But before we do that, we have to do substance R. Okay. But before we do substance R, go ahead and type in a question if you have one, something you want me to reinforce. Melissa, you asked me where did you get 250 calories from? And the answer to that is I just chose it. That exchange quantity, you can make it anything you want. And if your numbers work out good, it'll help you um, quite quite nicely. All right. So I said, well, let's try, 250 calories. And if it works out, if it's too much, my delta T's will be too big and it won't work. If it's too small, I'll have to do too many delta T's, and I'll have a long, long, long calculation. And there's no way to know ahead of time. You just got to try it out. Okay. So you could have tried, 500, or 25, and so H doesn't have a higher temperature than R. H starts at 805, Sophia, and R starts at 922. Right? Remember that? Right. So H is the cooler, or excuse me, H is the cooler, and so it absorbs a certain amount of energy. Whatever I try, Melissa, the reason that you want to make a guess is the amount of energy exchanged by nature does come in little bundles, but they're so small that it's extremely impractical to use that. It would be some really, 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 really small fraction of a calorie. So you have to do, a zillion calculations. But that's how nature works. Nature does it automatically. We have to, kind of use a little bit more finesse. Okay. Yep. You have to guess. And if you have it on the exam, yeah, you have to check. Yeah, it's always good to check your answers and stuff. So hopefully you make a good guess and it helps you work quickly. All right. So don't be too nervous about that. All right. But yeah, you do want to make, just a good a guess, and you'll know immediately if you know the size of the gap that you're trying to close. You'll know immediately if your delta Q is too big or too small, because it will give you delta T's like here, 10.1. That's not bad. We have a temperature gap of 117, right, from 805 to 922. And if we exchange in bindles of 10.1 Kelvin, that's not bad. We can cross the gap with that without doing a huge number. But let's figure out what substance R is. Substance R might be a little bit too small. Let's figure it out, okay? So let me ease this over here. Okay, so now substance R is the hot stuff, so it loses 250 calories, so that's negative 250. And then its mass, as usual, is 41 grams, okay? And the specific heat for this mysterious substance, 0.336, all right? So the first thing you do is multiply 41 grams and 0.336 calories per gram Kelvin, okay? And that's what you get in this next line. You haven't done anything with the 250 calories, but you have combined the two numbers on the right. So that's 13.776 calories per Kelvin. Okay, so Kelvin is in the denominator. And then we have to use that to figure out delta T subscript R, the change of temperature of substance R. So as before, we divide both sides by that quantity on the right. And in this case, it's 13.776. And when you calculate that out, you get negative 18.1 Kelvin. So that means that substance R really dips down it cools off by 18.1 Kelvin. So substance H, a little bit tougher to warm up. Substance R, you know, so calorie for calorie, substance R cools off more than substance H warms up. And we're going to use that when we do our calculations, right? So these are the two step sizes. Okay, we're going to step downward from 922 in units of 18.1 Kelvin, in steps of 18.1 Kelvin downward. And from 805, we're going to step upward by 10.1 Kelvin. Right now, let me go to the next page and show you what I mean. Okay, here are the, let me move this out of the way. Okay, so here's down here on the left, that's the initial temperature for substance H. Over here, 922, that's the initial temperature for substance R. Now, somewhere in the middle here, we're going to figure it out. Somewhere, maybe over here, maybe way over here, maybe somewhere in the middle. And the way that we do that is by taking steps. Now, we'll start with some steps for substance H. Okay, so there's my first step. We've exchanged 250 calories, plus or minus, and so substance H goes up by 10.1. All right, now what that means is your new temperature is 815.1. All right, let's do another one. Okay, because we're trying to cross this gap and meet in the middle somewhere, but it's still kind of poking along. All right, here's another exchange of 250 calories, and it increases by 10.1 again, so that's 825.2. All right, now let's do some for substance R. Now this one dips to the left, and it cools off by 18.1 Kelvin. All right, and wait a minute, let me look at this. Okay. So that means your cool off after one exchange of 250 calories, substance R is all the way down to 903 already, right? Now, second exchange, another 18.1 Kelvin negatory, and now you're down in 800s, 885.8, right? And you can see that we're closing the gap, right? We still have a few exchanges to go, right? Let me do another one over here. Okay, so that's another 18.1 downwards. So that puts me at 867. All right, let's do one over here for substance H. Another 10.1, that puts me at 835.3. All right, now instead of 118 or 117 that we had initially, now we're down to about 32.4 Kelvin. So we're closing the gap. All right. So probably we're going to need to do at least one more. All right, so let's do another for substance H. That adds 10.1 Kelvin. So now we're at 845.4. All right. And let's do a one for substance R. Okay, there's another 18.1. And now we're really getting close. All right, now we've got a gap there, and we can't do any more of these exchanges. All right, but we've done 4 exchanges of plus or minus 250 calories, pluses for substance H, minuses for substance R. Substance H has warmed up nicely, about 40 degrees. Substance R has cooled off even more, 70-something degrees. So that's good. But we're still not quite at equilibrium. Okay, we have a little gap there, 4.2. Now our plus 10.1s and our minus 18.1s are too big for that gap. So what we can do is try a slightly different delta Q one time. Okay. Now an easy one is to take whatever you used the first time, divide it by 10. Okay, so 25 plus or minus 25 calories. And all that means is that your delta T's are 1/10 of what they were, right? So for substance H, instead of going up 10.1 Kelvin, you go up 1.01 Kelvin when you exchange 25 calories. For substance R, instead of dipping down by 18.1, you dip downward by 1.81. All right, now let's do one of those for each of these. All right, here we go. Okay, there's 845.4. So that takes me to 846.41. All right, and here's one exchange of minus 25 calories for substance R. And that dips me down to 847.79. All right. So now we're cooking. All right. Now we're getting really close. And we're basically done, and I'll show you why. This thing rounds to 846. Right? It would round down to 846. This one would round up to 848. So that means that our equilibrium temperature it's going to be somewhere between those two. So the whole number that's between 846 and 848, 847. And there you go. If you want to get closer, you can do, instead of plus or minus 25, you can do plus or minus 2.5. And that'll inch you a little bit closer. But this is good enough for us. We can make an estimate to the nearest Kelvin with this. Okay, now let me pause and see if you have a question or so. And what Nathan wrote down is very good. That's exactly what you got to do. And he's explained it a little bit differently than I do, so that's good. It's sometimes nice to get two different explanations. Andrew, I just did explain it in English with pictures. So try to do your best with it. Okay. And this is being recorded so you can review it later on. It's work it out on paper. What you see in the YouTube lectures is doing it with a list. So this is numerically the same as using a list, but we're doing it horizontally with a little line segment and stuff like that. So Brianna, is it always going to ask for the nearest Kelvin on the exam? Well, I'm not going to tell you that you're going to have this on the exam, but if you did, yes. Nearest Kelvin is good enough for us. Okay, sometimes I ask for nearest 10th of a Kelvin, but I think on the exam, if I do have a problem like this, one plus or minus 1 Kelvin is good. Okay, just remember the conversion for Kelvin is right. Okay. Okay, thanks, Brianna. All right. All right, another question. Okay. Sophia, it should be uploaded by about 2. Although sometimes it takes YouTube to a little bit of time to process it, but it'll be there this afternoon. All right. All right. Let's go to the next slide. And I want to talk here about the linear charge array. Some very simple examples of this are in the last lecture and also the last homework. Okay. Now this is a linear charge array. The electrons are charges The protons are positive charges, and they're all arranged in a line. Now, in this class, this is a brain burner, and it's something I want all the students to try to tackle. And I always set it up under the following conditions. It's linear, it's all on the same line, okay? And they're equally spaced, all right? Now, if they're differently spaced, or if they're shaped into a square or something like that, a little bit more difficult, you gotta use trig and stuff. But this, you don't really need to use trig, you just have to use left and right, minus signs and pause. I'm still recording here. I'm sorry, I'm in my living room and there's a little bit of noise. Okay, so those are the conditions in a straight line and equally spaced, and that makes things a little bit easier. Right now, what you want to remember is if you're, for instance, if you're focused on this particle on the left, the electron, and how many newtons it gets in total, you have to figure out how many newtons it gets of repulsion from this nearest neighbor, the electron, how many it gets of attraction from the second neighbor out, that's the proton, how many it gets from the third neighbor out, this proton, also attraction. So you have to keep in mind a couple things. You know, for the particle that you're in consideration, is it getting a repulsion from any of its neighbors? And is it getting an attraction from any of its neighbors? And here we got a mixture, okay? So the repulsions are gonna be to the left. The particle itself that we're focused on is on the left. So if it gets pushed away from the array, it's gonna be to the left, all right? So the nearest neighbor interaction between electron, the electron that we care about here on the left, and the nearest neighbor, it's going to be like an arrow like this. Okay, so let's let that arrow, it's 200 pixels long, and it's to the left. Now that's going to be the biggest force from any of the other three, because the electron right here, the second electron, is the closest of the other three. But the proton here in position number 3, this is the second neighbor out, it's going to attract the electron, you know, so it's going to have some rightward newtons, so, but it's not going to be as big because it's further away, right? And then this final proton out here, it's going to have an attractive pull on this electron out here that we're studying. And so it's going to have a few newtons out here, right? So I kind of stacked them up vertically so you can compare the sizes. So remember, you have to get the size and you have to get the direction. And then you have to add them up, okay? Now, if this one here, this big blue arrow, if I say, all right, let's think of that as 200 newtons of repulsion, you know, and we could have that, that would be normal, okay? That's gonna be, so that's like a negative 200 newtons, okay? And the two red arrows are gonna be positives, and because this proton, neighbor number 2, is twice as far away, its force of attraction is 1/4 of the nearest neighbor force. And it's because it's a proton, it's in the opposite direction, right? So the size of this force is controlled by the distance from your target particle. So our target particle is over here on the left, and nearest neighbor, that's 1 unit of distance. Second neighbor, this proton, that's another unit of distance. So it's twice the distance. And so it's 1/4 of the attractive force as the nearest neighbor. So 1/4 of 200 is 50 newtons. It's an attraction, so it's to the right. Right now, way up here, I've got this little teeny vector up here for the repulsion from the last neighbor, the third neighbor out. You know, he's in the mix as well, and but he's 3 times as far away as the nearest neighbor. So nearest neighbor distance is right here. That's 1 unit of distance, which I haven't marked, but you could, you know, I sometimes have diagrams with the distances marked out symbolically. Okay, so The last neighbor is 1 unit, 2 units, and then 3 units. So his distance is 3 units out. So his electromagnetic force strength is going to be diluted by the square of 3, so 1/9. All right, so it's dipped down to 1/9 of 200, and that works out to about 22.2 newtons. It's attraction to the right. So to calculate this, you would go negative 200 plus 50 plus 22.2. And then that would be your, and it's going to be a negative number. Let's figure it out here. Negative 200 negative plus 50 is negative 150. Negative 150 plus 22.2 is, let's see, what is that? Negative 150 plus 22.2. That's 28, 27.2. Anybody verify me on that? Hey, negative 200 plus 50 plus 22.2. Anybody verify me on that? 72, 72.2. So that's 27.8. So this should be negative 127.8. Andrew, double check that. It should be negative 200 newtons. So you should have 127.8, and it should be negative 127.8. Anybody else verify me on that? Okay, it should be like this. Minus 200 newtons plus 50 newtons. Okay, wait a minute, let me do this. Minus 200 newtons plus 50 newtons plus 22.2 newtons. Yeah, okay, good, Chidima. Good, good, good. Yeah, all right, so, okay, good, you guys are verifying me, great. All right, so that gives you the basic strategy. Now, I don't think you have actually 4 particles on the homework. I think you only have 3. But you still have to decide, is the constituent force, like the big blue one, is it leftward or is it rightward? And that depends on, is it a attraction or a repulsion? And then you got to make the same decisions about the second neighbor. Okay, in this case, the red arrow for 50 newtons of attraction. Now, you may not have electrons on the left, you may have a proton on the left. All right, so you just got to, study what you got and then make your decisions. Is it an attraction? Is it a repulsion? Is it leftward or is it rightward? And then what is the size of it compared to the nearest neighbor? So I'm always going to give you the nearest neighbor force of interaction. Like in this one, I said, let's say that this is 200 newtons of repulsion for the nearest neighbor interaction. And I'll always give you that. So then all you have to do is figure out the other, the second neighbor, third neighbor, and so on, and then add them up. All right. Now, let me see here. Okay. Now, that's all I have for today. Ooh, we're a little bit over time. Departing questions, just to double check before Tuesday. Go ahead, Audra. Oh, you don't have a question. Okay, nobody has questions? All right. I'll be uploading this into YouTube in just a few minutes. And so study hard over the weekend. And remember, after exam 3, that's when we do this special maneuver with your grades. We drop your lowest midterm and we keep your best 2. All right. So after exam 3, we can do that. All right. So after Tuesday next week, that'll be helpful. Okay. Kahoots. I know nothing about Kahoots. I think I used those once. Okay. All right. I'll see you guys later. Good session. Let me pause the recording.